2. Chalmers breaks barriers in quantum error correction. 3. Breakthrough in quantum computing, scientists simulate the impossible. 4. Simulating error-proof quantum machines, a breakthrough in quantum computing. 2. Chalmers breaks barriers in quantum error correction. Quantum computing's biggest challenge just got a major breakthrough, but here's where it gets controversial. July 2, 2025, quantum computers hold the promise of revolutionizing how we solve some of the world's toughest problems, from drug discovery to cryptography and artificial intelligence. Yet, despite their incredible potential, these machines are still grappling with a critical obstacle: their fragile nature and the difficulty in correcting errors that inevitably arise during quantum calculations. To build truly dependable quantum computers, scientists need to simulate these quantum processes on classical computers to verify their accuracy, a task that has proven to be extraordinarily complex and resource-intensive. Now, a pioneering team of researchers from Chalmers University of Technology, the University of Milan, the University of Granada, and the University of Tokyo has developed a groundbreaking algorithm that can simulate a special class of error-corrected quantum computations. This achievement marks a significant milestone in the ongoing quest to create robust and reliable quantum technologies. Quantum computers are expected to outperform even the most powerful supercomputers available today by tackling problems that are currently unsolvable. Their future applications could transform fields such as medicine, energy optimization, secure communications, artificial intelligence, and logistics. However, the path to these breakthroughs is blocked by a fundamental challenge: quantum bits, or qubits, are extremely sensitive and prone to errors caused by environmental noise and other disturbances. Unlike classical computers, which can quickly detect and fix errors using well-established methods, quantum computers face a far more daunting task. The errors in quantum systems are not only more frequent but also harder to identify and correct because of the delicate quantum states involved. As a result, current quantum devices lack fault tolerance, meaning they cannot yet guarantee reliable, error-free computations. To ensure that quantum computations are performed correctly, researchers rely on simulating these quantum processes on classical computers. This simulation acts as a benchmark to check the quantum computer's output. One of the most important types of quantum computations to simulate are those that incorporate error correction codes, which help quantum computers resist noise and maintain accuracy. However, simulating these error-corrected quantum computations is incredibly demanding, so much so that even the world's fastest supercomputers would require an impractical amount of time, sometimes longer than the age of the universe, to complete the task. The team from Chalmers, Milan, Granada, and Tokyo has now become the first in the world to introduce a method that can accurately simulate a particular kind of quantum computation known for its error-correcting capabilities but previously considered too complex to model effectively. This breakthrough addresses a long-standing bottleneck in quantum computing research. We have found a way to simulate a specific type of quantum computation that previous techniques could not handle, explained Cameron Calcluth, PhD in applied quantum physics at Chalmers and lead author of the study recently published in Physical Review Letters. This advancement allows us to simulate quantum computations that use an error correction code essential for fault tolerance, which is a critical step toward building more reliable and scalable quantum computers. Why error correction in quantum computing is both vital and challenging. The root of quantum computers' error problem lies in their fundamental units, qubits. These qubits harness the quantum phenomenon of superposition, enabling them to represent both 0 and 1 simultaneously, as well as any combination of these states. This property allows quantum computers to process information exponentially faster as more qubits are added. However, this power comes with a catch: qubits are extremely vulnerable to external disturbances. Even the tiniest environmental noise, like vibrations, stray electromagnetic waves, or slight temperature fluctuations, can cause qubits to lose their quantum state, known as coherence, Calcluth said. When coherence is lost, the qubit can no longer perform accurate calculations, which undermines the entire quantum computation. To combat this, scientists use error correction codes that spread quantum information across multiple physical systems. This approach enables the detection and correction of errors without destroying the fragile quantum data. One promising technique involves encoding quantum information into the many energy levels of a vibrating quantum system, known as a bosonic code. However, simulating quantum computations that use bosonic codes has been notoriously difficult because of the infinite or very large number of energy levels involved. Until now, conventional computers have struggled to simulate these codes reliably. A new mathematical approach unlocks simulation of GKP codes ***. The researchers' novel algorithm focuses on simulating quantum computations that employ a specific bosonic code called the Gottesman-Kitaev-Preskill (GKP) code. This code is widely used in cutting-edge quantum computing experiments because it helps protect quantum information from noise, making quantum computers more resilient. GKP codes store quantum information in a way that makes error correction more feasible, reducing sensitivity to noise and disturbances, said Giulia Farini, Associate Professor of Applied Quantum Physics at Chalmers and co-author of the study. However, their deeply quantum nature has made them extremely challenging to simulate on classical computers until now. We have developed a unique mathematical tool that allows us to simulate these codes much more efficiently than previous methods. Thanks to this new algorithm, researchers can now more reliably test and validate the results of quantum computations that use GKP codes. This capability is crucial for advancing the development of stable, scalable quantum computers. Our breakthrough opens up entirely new possibilities for simulating quantum computations that were previously out of reach, Farini added. This is a vital step toward building quantum machines that can operate fault-tolerantly and at scale. But here's the part most people miss ***. While this development is a huge leap forward, it also raises important questions about the limits of classical simulation and the future of quantum advantage. If classical computers can simulate certain error-corrected quantum computations more efficiently than expected, what does this mean for the timeline of quantum supremacy? Could this blur the line between classical and quantum computing capabilities, or does it simply highlight the need for even more advanced quantum error correction techniques? We'd love to hear your thoughts. Do you think this breakthrough challenges the idea that quantum computers will soon outperform classical ones, or is it just a necessary step on the road to truly powerful quantum machines? Share your opinions and join the conversation below. For those interested in the technical details, the full scientific article can be found here. Classical simulation of circuits with realistic odd-dimensional Gottesman-Kitaev-Preskill states, https://journals.aps.org/pl/abstract/10.1103/xmtw-g54f. Source: Lovisa Hackinson, Chalmers University of Technology, https://current/forward/double-www.chalmers.se/en//current/unique-method-enables-error-correctable-quantum-computers. 3. Breakthrough in quantum computing, scientists simulate the impossible. Imagine a world where quantum computers operate flawlessly, solving problems that today's supercomputers can't even dream of tackling. But here's the catch: quantum systems are notoriously error-prone, and fixing those errors is a monumental challenge. Now, a groundbreaking achievement by researchers from Chalmers University of Technology in Sweden, alongside teams from Milan, Granada, and Tokyo, has cracked one of the most perplexing puzzles in quantum computing. They've devised a novel method to simulate error-corrected quantum computations, a feat once deemed practically impossible. This milestone brings us one step closer to building quantum machines that are both powerful and dependable. Quantum computing promises to revolutionize fields like medicine, energy, and artificial intelligence, but its potential is currently held back by a critical hurdle: errors. Unlike classical computers, which can swiftly detect and correct mistakes, quantum systems are fragile. Their quantum bits exist in a delicate state of superposition, allowing them to represent both 0 and 1 simultaneously. However, this very sensitivity makes them vulnerable to even the smallest disturbances, such as temperature fluctuations or electromagnetic interference. As Cameron Kalkluth, a quantum physicist at Chalmers, explains, the slightest noise can cause qubits to lose their coherence, effectively halting calculations. This fragility has made error correction a holy grail for quantum researchers. To ensure quantum computations are reliable, scientists often rely on classical computers to simulate these processes. But simulating quantum behavior, especially with advanced error correction techniques, is no small task. In some cases, it would take even the fastest supercomputers longer than the age of the universe to complete such simulations. That's where the recent breakthrough shines. The team developed a groundbreaking algorithm to simulate a specific type of error-corrected quantum computation using bosonic codes, a method previously thought unmanageable for classical systems. Bosonic codes, like the Gottesman-Kitaev-Preskill (GKP) code, encode quantum information across multiple energy levels of a quantum system, making them highly resistant to errors. However, their complexity has made them notoriously difficult to simulate. Giulia Farini, a co-author of the study, highlights the significance. GKP codes are deeply quantum mechanical, which made them extremely hard to model. Now, we've found a way to simulate them far more effectively than ever before. This innovation opens the door to testing and refining quantum algorithms that were previously out of reach. The researchers achieved this by creating a new mathematical tool, enabling more accurate validation of quantum computations. As Farini notes, this paves the way for entirely new methods of simulating quantum processes, essential for building stable, scalable quantum computers. The study, published in Physical Review Letters *, details their method and its implications for the future of quantum technology. But here's where it gets controversial: could this breakthrough lead to unintended consequences? For instance, if error correction becomes too efficient, might it inadvertently stifle the development of alternative approaches? Or does this advancement finally tip the scales toward practical quantum computing? We'd love to hear your thoughts in the comments. What do you think is the biggest hurdle left in quantum computing, and how might this research reshape the field? Share your perspective and join the conversation. 4. Simulating error-proof quantum machines, a breakthrough in quantum computing. Unlocking the secrets of error-proof quantum machines. Imagine a world where computers can solve complex problems that are currently beyond our reach. Quantum computers, with their incredible processing power, promise to revolutionize fields like medicine, energy, encryption, artificial intelligence, and logistics. But there's a catch: these systems are prone to errors that are difficult to detect and correct. In fact, the slightest noise from the surroundings can cause the qubits to miscalculate or even lose their quantum state. The verification challenge ***. Researchers have been struggling to verify the accuracy of quantum computer calculations using conventional machines. The task is so computationally demanding that even the world's most powerful supercomputers would need the age of the universe to reproduce quantum results. But a team of scientists at Chalmers University of Technology and international partners has cracked the code to simulating error-proof quantum machines. The breakthrough ***. The researchers have developed a method to simulate quantum computers that use specialized error correction codes called Gottesman-Kitaev-Preskill (GKP) states. This approach is crucial for building fault-tolerant quantum systems that major tech companies and research labs are actively pursuing. The team's key innovations include creating a specialized algorithm that can handle the infinite energy levels inherent in GKP codes, developing the Zach-Gross-Wigner function, and establishing efficient methods to simulate up to 1,000 quantum modes with minimal computational overhead. Why error correction matters ***. Quantum computers derive their power from qubits that can simultaneously hold multiple values through a phenomenon called superposition. This creates exponential computational capacity as more qubits are added, but also makes the systems extremely fragile. The slightest noise from the surroundings can cause the qubits to miscalculate or even lose their quantum state, their coherence, thereby also losing their capacity to continue calculating. Practical impact for quantum development ***. The simulation method proves particularly powerful for highly squeezed quantum states, those with precisely controlled properties that are essential for fault-tolerant quantum computing. For states with 12 decibels of squeezing, considered necessary for practical quantum error correction, the algorithm can simulate circuits with up to 1,000 modes using less than double the computational resources needed for a single mode. This efficiency represents a dramatic improvement over existing approaches and could enable researchers to validate quantum computer designs before building expensive hardware. The future of quantum computing ***. As quantum computing moves from laboratory curiosity toward practical application, tools like this simulation method become essential for ensuring these powerful machines work as intended, bringing reliable quantum computation closer to reality. The method also provides a pathway for benchmarking early quantum processes and understanding how different error correction strategies perform under realistic conditions. Join the conversation ***. What do you think about the potential of quantum computing? Share your thoughts in the comments below. Do you think this breakthrough will accelerate the development of reliable quantum technologies? Let us know.